in the right order. So then VF dot VI, negative VI dot VF, and then negative VI dot VI. And then slap a plus sign in
write
it.
it like that? The way you have it up on the top?
Wait, say it again?
Do I have to write it that way? You have it up on the top?
Well, I'm gonna use this to, we're gonna get rid of two of these. So another question? All right, so let's talk about a vector times itself using a dot product. Think about when we were doing that 5 Newton force in the direction of the 3 meter of movement. You just multiply the numbers. If they're in the same direction, you just multiply them. Now, over here, I got a vector in the exact same direction as itself. It is impossible for any quantity not to be in the same direction as itself. Whichever direction this velocity is, the other one, same way. So I'm just going to multiply the magnitudes. So this is just VF squared. And at this point, the vector symbol goes away. So any vector dot product with itself is just whatever the magnitude is squared. This right here and this right here are going to cancel out. Order doesn't matter. 2 times 3 is the same as 3 times 2. It's called the commutative property. Commutative property of multiplication holds. This and this are the same thing, and I'm subtracting. Get a big goose egg right there. I guess in the box chart here, we're getting rid of those. And then the last bit, I've got something with itself, it's plus 0, minus VI squared. All right. Now, some of this were leaps. With, just so you know, with trig, it becomes a little bit easier to go over this, but beyond the scope of the course, I just want you to understand where the equation we're going to get to, I think in 2 steps, comes from. Maybe 3 steps. Or at least convince you that it comes from somewhere. It's not that Hewitt sat down and said, hey, I'm just going to make stuff up.
I think he did.
That's possible. But so we started out with work. This is the total work. Is equal to 1/2 times the mass times VF squared minus VI squared. Just rewriting what I had right here, just got rid of the 0. I'm now going to distribute. I'm going to take this and multiply times the first term, and then multiply times the second term. So this is 1/2 in the final squared minus 1/2 in the initial squared. You're so close to the end. 1/2 NV squared shows up twice. To the point where they said, you know what? Let's just come up with another letter to represent that whole thing. The letter K makes sense to them. There's some sense to it. So they're going to let big K equal 1/2 NV squared. So this work total is just equal to this big K final minus the big K initial, which is just change in big K. Does it seem strange that I just threw in another letter just for the fun of it?
That's why I said, this is why it looked like he just threw stuff together.
Yeah, you know, there's a point to it.
Okay, so wait a minute. So we multiply 1.5 times VF1 minus V, well, it's separately. And then that got us the bottom one, that's half MV and squared.
Right.
And then minus 1/2 MV squared. So put all that together, that's why we got that bottom one?
Yep.
I just swear, I don't drink enough water.
All right. Now, what does this mean?
Potassium.
Don't look at me, I didn't say that.
Smart.
Bring in your chemistry stuff and do
Well,
physics.
I said we got biology students in here, that's exactly what that was. Action potential. That's
K is periodic table.
All right.
No, that was a biology student, she was talking about, actual potential, ouch.
We don't need to look at the periodic table right now. This is not K for potassium. I know, it doesn't work on the weak-minded, but.
It is copyright.
Alright, so what we end up with there is, I'm just gonna basically write what I have over there, except I'm gonna cut out that middle section. Work total is equal to this change in big K. Big K actually has a name other than big K. This big K right here is kinetic energy.
Kinetic. Okay.
So K for kinetic. Let that sink in for a moment, then I'm gonna let you know the one formula that you will need to have memorized.
As long as I'm down with these formulas.
You can handle it. All right, so you were working on your Nobel Prize winning work in physics. The formula for kinetic energy is 1/2 mv squared. You're in physics 110. The formula for kinetic energy is 1/2 mv squared. All the other formulas, there's gonna be slight tweaks to them as we go. F equals ma turns out that's a specialized case of constant mass. If the mass changes, there's a more generalized formula that is used. But kinetic energy being 1/2 mv squared, that is gonna be a constant. Sorry, it's a constant formula, there's no tweaks to it. So, if I ask you, what is the formula for kinetic energy? In unison, all of you are to reply 1/2 mv squared. Now sometimes students decide that they want to go the long route and do 1/2 times mass times the speed squared. Don't. If you want to do that on an individual, that's fine, but as a group, the answer is 1/2 mv squared. Now, before I then ask you what's the formula of kinetic energy for you to sing back with the chorus of angels, what the answer is, just a little bit of the story here. When I was first started working for Anderson Consulting, we were in what they call boot camp, and we were all busily typing, and at some point these two people came in and said, all right, everybody stand up, jumping jacks. And I being one of them, looked at them strangely, wondering why on earth would I want to do that? And then her tone of her voice changed, and she said, I'm serious, get up, we're doing jumping jacks. So, I want all of you to respond 1/2 mv squared, and I am serious, I do want you all to do it. And in unison would be absolutely spectacular. What's the formula for kinetic energy?
1/2 mv squared.
That was nice. To various points during the course, I will ask you again. Now, 30 years from now, when I run across you, assuming I'm going to be, my vision's probably going to be gone, but my hearing's going to be gone almost. But enough, I'm going to recognize you. I should be able to ask you, what's the formula for kinetic energy? And I expect you to know it 30 years from now. All right.
Do you know if person knows what kinetic energy is?
It is the energy of kineticism. All right, so let's actually talk about what this is and who cares. From a physics point of view, I'm not going to make judgments upon your own view of it.
Okay.
This course is a classical physics course. In classical physics, you can be guaranteed that all objects have three things. All objects have a speed. That speed could be 0, but it's still a speed. All objects have a position. They are somewhere, and all objects have a mass. The physicists, probably natural scientists at that point, have an energy to represent each of these. Speed is represented by kinetic energy. Position is represented by what is known as potential energy. And mass is represented by what is known as rest energy. The symbol for potential energy. I think Hewitt uses PE. I tend not to do that. I prefer to use a single letter. Now, the letter I'm going to be using, I believe, comes from the German, but I'm not 100% sure of that. But the letter that's commonly used is the capital U. Rest energy, represented by E with a little subscript R there. I want to talk a little bit about rest energy right now. Rest energy is not something we're going to spend much time on, but I at least want to introduce you to it, so later on, if it does come up, you go, wait a second, I know I've heard that before. Or better yet, you go, oh, let me tell you about rest energy. Most of you know the formula for rest energy, even though if I said write down the formula for rest energy, you probably would go blank and not know. But you do know it, and I'm going to start you out, and you're going to fill in the rest. E equals, there you go. The one adjustment to that, and that's a 2 there, one adjustment to that is you put a little subscript 0 next to the mass, because this should be the rest mass. Now, rest mass is not something new. It's something that you've been working with all this time. Whenever you've found the mass of an object in the lab, you're actually finding its rest mass.
Mister, when did we learn E equals MC squared up? Because I felt like I know it, but I don't know how.
It, for some reason, is the most famous. Yeah, it's Einstein. It's the most famous equation in physics. I don't know why it's more popular than F equals MA.
Okay. All right.
Have a good one.
But apparently it's controversial enough for students to storm out.
I heard that.
No,
Okay.
it turns out the faster you get, your mass changes, and I'll stick with that. Your mass changes, and so E equals MC squared actually takes into account kinetic and rest energy. That's well beyond the scope of the course. I at least just wanted to get it out there, and that probably is, potentially is the last time we talk about rest energy, other than this thing that just occurred to me. Mass and energy started out as completely separate entities. Einstein was the one who came up and realized there was a connection. If you go far enough in physics, you get to a point where mass and energy are almost used interchangeably. If I take a match and I get a really good balance, but I find the mass of this match unlit, unstruck, and then I strike it, capture all the ash that comes off of it, find the mass of the ash that come off of it, and what was left over from the match itself, there's a small difference in the mass. That small difference in the mass was converted from mass into energy. Atomic bomb and hydrogen bombs are classic of, you take an atomic bomb, you take the uranium atom, you split it, the two pieces that you end up with is less mass than what you started with. That difference in mass is what went into the energy. Hydrogen bomb, you take two hydrogens, slam them together. The mass of what you have after you slam them together is smaller than the two separate ones. And that difference in energy and that difference in mass goes into energy and the explosion.
MC is change in mass?
M is the mass, C is the speed of light squared. C is approximately equal to 3 times 10 to the 8th meters per second. 300 million meters every second. Right. Chapter 7 does not deal with rest energy. Again, just bonus knowledge. Chapter 7 concentrates on these two things. The combination of them can be referred to as mechanical energy. Now, usually, at this point in the course, he could just say energy, and you should okay, I'm assuming he means these two things. There are some questions that, if I recall correctly, where he actually refers to mechanical energy, all he's referring to is the kinetic and the potential. So the mechanical energy is just whatever the kinetic is plus whatever the potential is. Kinetic energy plus potential energy.
Why you put E?
For the mechanical energy.
Oh. I knew that.
The MC squared thing, that's beyond the scope.
Oh.
Let's get rid of that rest. Now, I know you're gonna be excited by this, so more vocab words. I do need to talk about two other kinds of work. Actually, two different kinds of forces. There is something known as a conservative force. Conservative force does conservative work. And then if it's not conservative, they got clever on this one, non-conservative. There is a formal definition of these. I am not going to go into it. It is calculus based. But I'm going to write out all of the conservative forces we have covered so far. Done. We've dealt with one conservative force, gravitational force. Weight is a gravitational force. Weight counts as part of this. There is another conservative force that we will definitely be getting to in this course, and that is elastic. An elastic force, I guess I should say ideal. Ideal elastic force is also a conservative force. That is something that we officially hit in chapter 14, somewhere around there. I guess I already handed those back, so I don't need that. Okay. Potentially, we get at the end electric force and magnetic force. And that's it for the course. Those are the only ones. Right now, gravitational force is the only one we've covered so far. Everything else falls here. Friction is the classic non-conservative.
But give me an example of everything else.
Friction.
Oh.
Normal.
Tension. Oh.
Most likely other, but that depends on the problem.
Okay.
All right, ask you to use your imaginations here for a moment. See if someone's willing to take a leap. Why do you suppose it's called a conservative force?
It doesn't have liberal views.
I'm just gonna let that hang there. All right. As a hint, it's not a political statement. Or
When I
something.
think about like conserving something, like I can't really explain it, I think, but
All right, so you hit upon a key word there, conserving something.
yeah.
What is being conserved?
Energy?
Energy. Conservative forces conserve energy.
Teamwork.
Yeah.
Now, what conservation of energy means in physics is not the same thing as conservation of energy in environmental science. I think for the most part, conservation of energy in environmental science, and I'm going to oversimplify it, is trying to basically leave as small a carbon footprint as possible, use as little energy as possible. Conservation of energy in physics is whatever energy I started with, I have the exact same amount at the end. It is no loss whatsoever, no loss, no gain.
Like what you just said.
Conserving energy in physics means that our total energy, total mechanical energy, stays the same. This is one of those, there's a couple fundamental conservation laws. There's conservation of momentum, which we've done, conservation of energy, conservation of angular momentum. These are all fundamental principles in physics. In essence, all stemming from Newton's laws. All right, another chance to take a wild guess here. What do you suppose non-conservative forces do? Yeah, there we go. So, now let's connect the work with the stuff we just did. The work total, I'm gonna write net here just because it's fewer letters. The net work is equal to the net force times displacement. Conservative work, so the little c there stands for conservative. Conservative work equals the conservative force times displacement. Non-conservative work is equal to non-conservative force times displacement.
Is X always gonna be displacement?
Delta x,
Delta X.
I use it quite a bit. There's a good chance that I'm gonna probably use it for 99% of the time, but sometimes I throw an S or an R in there instead of an X, just to mix it up. Sometimes I'm in that mood. I'm in an S mood.
Alright.
All right, I'm about to do another, it's a smaller derivation here. We have the total work is equal to the change in kinetic energy. That is the work energy theorem. I think I mentioned it verbally, but didn't write it down. This is known as the work energy theorem. The net work, the total work is just, well, I have only two types. It's either conservative or non-conservative. So this is my conservative work plus my non-conservative work. That's just my total work. Non-conservative work causes change in energy. So work conservative plus my change in energy is equal